Hello everyone, my name is Dr. Rajat Dandekar and today I am going to talk about a very interesting topic. All of us have seen movies where we have seen robots being trained and doing some incredible stuff out there in the world. The first thought which comes to mind is the movie Terminator. There are a lot of other movies which have extrapolated the capacity of artificial intelligence being embedded in robotics in such a way that these robots can actually now go out in the world and do tasks, household tasks, or rather complex tasks. Many movies even envision these robotics in armies. A very powerful robot can strengthen your army a lot. And in most of these extrapolations, we have seen that these are intelligent robots, which means that they understand the world around them, they perceive their world around them, and based on this perception, they are able to take smart actions. This is the world everyone is envisioning that we will go to this world in the next maybe 15 or even 20 years, or even less than that. The question is, how much do you think is the gap between where we are at now and where we want to go? The place where we want to go is every household has a mini robot which can do household chores like folding clothes, doing dishes, laundry, etc. Then why is that we don't even have these robots in our houses now? If robotics, the future of robotics is so promising, why don't we see these household robots being used by people very commonly? The recent launch of the Neo robot comes to mind, where the initial advertisement was huge. They claimed that this robot can fold your clothes, do dishes, open doors for your guests, etc. But when you look at their video closely, you see that the robot is largely teleoperated. It's not very smart, and you see that okay, this is maybe largely a marketing gimmick, and the actual things that the robot can do are limited in nature. So why is there such a big gap between even a robot that can fold clothes is not possible to us these days? And then on one hand, we think of these Boston Dynamics type robots which can do acrobatic stunts. They can do somersaults. They can do a lot of stuff, right? So on one hand, we believe that the future is promising, and then on the other hand, we don't even have a robot which can fold our clothes. So that leads us to think that robotics is a field which is evolving, but at the same time, it's not evolving at the same pace as artificial intelligence. Now, the reason I'm recording this video is because I want to bring all of your attention to where the field of robotics is now, what are researchers thinking, and where the field is going towards. The first thing that we see, which is different right now compared to what was the situation 5 years or 10 years back, is the development of large language models. LLMs have proven to be incredibly successful at reasoning and doing a lot of complex tasks. So naturally, one tends to think that why can't we leverage the power of LLM inside a physical manifestation of the LLM, which is the body of the robot. And this is what I'm going to talk about today. But before we get to that, let's understand very briefly how the field of robotics has evolved. The field of robotics started with classical robot learning. What does that mean? You see, I have a robot here in front of me now. This robot has 6 degrees of freedom. The first degree of freedom is this arm which moves up and down. Then you have this gripper which actually rotates. And then you also have this pick and place capability where this gripper moves up and down. So these are 3 degrees of freedom. The fourth one is over here. There is another arm which moves up and down. The fifth one is this. And what is the sixth degree of freedom? This robot can also move sideways like this. So there are 6 degrees of freedom in which we can move this robot. Now in classical robotics, what happened is that this is the gripper which we want to move to the desired location. And these are the arms which connect from the base of the robot to the gripper. What people did was that they wrote down mathematical equations to predict the position of this gripper dependent on the angles of these joints. So if you have a trajectory in which you want to move this gripper, you give that trajectory to your model and your model will predict all these joint angles. So this is how you will be able to move the robot according to a specific trajectory. Now, this is good, but the problem with this method is that the math becomes incredibly complex and it is not generalizable to complex scenarios, more real life cases where you will not have a simple trajectory, but the trajectory will be embedded with obstacles. There might be different situations which arise at the moment where the robot has to take quick decisions. So you immediately see the limitations of classical robotics. After classical robotics, the next field which came into the picture was reinforcement learning. Now, reinforcement learning offered something very different. It said that you do not need complex mathematical equations to understand the dynamics of the robot. You do not need these equations to map the input to the output. What you need is you need experiences. Allow the robot to interact with the environment, learn from the experiences which the robot gathers, and then improves itself from the experience which the robot has gathered. This is very intuitive for all of us because we have learned a lot of skills in life through this process. Imagine the first time in life we learned how to ride a bicycle. We made a lot of mistakes, but eventually we learned how to ride a bicycle. The same thing, but now replace us with a robot and replace the bicycle with the environments. So let's say the robot is learning to pick an object and place an object. Initially, the robot will make a lot of mistakes, but eventually it will learn from its experiences and understand how to pick and place the object. This is done with the help of a reward function. Now, here the robot is learning the policy, which means that for every state which it encounters, what is the right action which I should take. So reinforcement learning was incredibly effective from that perspective, but it also faced the major drawback that it was not transferable to a lot of different environments. Also, initially, when the robot starts to make mistakes, if it's a sensitive environment, you cannot afford to make these mistakes because there might be issues related to safety. So, reinforcement learning was great, but it had certain drawbacks. After that came the field of behavior cloning or imitation learning. Now, this was again a very interesting field because it said that don't learn from experiences, but you show me what do you want to do, and then my robot will look at these trajectories and then learn from them. This was very interesting. So for example, if you want to teach a robot how to pick and place an object, you just show the robot how to do it, and then the robot will learn from that. This is very similar to supervised learning in machine learning. So you give the robot a bunch of input-output pairs, and the robot learns a function which maps the input to the output. So the formulation looks kind of simple, but it's incredibly powerful. And behavior cloning is used in a lot of areas where reinforcement learning fails. Now, all these three methods have been incremental progress, and sometimes we use a combination of them, but they are not very effective for these modern robotic applications which can encounter a lot of different scenarios, and things are incredibly complex in the real world, right? This is where I'm coming to. Where the field is evolving since the last 5 years is very interesting, and this is largely due to the development of large language models. So let's understand how LLMs can be used in modern robot learning. What LLMs offer is that they offer a model which you can ask any question to any question in the world and it can give you an answer. Now, let's say there is some person sitting in some corner of the world who wants to impart intelligence to their software. They don't need to train the LLM again from scratch. Someone has already done it for them. They need to use the existing LLM and adapt it to their requirements. The question is, why can't we do something very similar for robotics? Why can't we build foundational robotics models? Now, what does a foundational robotic model mean? Foundational robotics models means that you have a model which is trained from incredible amount of robotics trajectories, huge number of data, and then the foundation model then becomes intelligent, that it understands that since it has seen all these scenarios before, it understands how to fold clothes, how to pick and place objects, how to do complex tasks like let's say fitting a belt over two gears. All of this has already been taught to the robot. So in an ideal world, this foundation model should be transferable from one organization to the other. Why do you need to train the robot again and again on these tasks? This is exactly where the field is moving to. And as we speak, there are a lot of foundational models being developed in a huge effort of different labs. People have put together data sets like OpenX, which has huge number of tasks which the robot has learned from, and these are transferable data sets. Now, from a philosophical point of view, it sounds great to have a foundational model and it makes sense, right? But the reason I'm talking this to all of you right now is that this is the time where people are building these models, and it's the right time to enter into the field of robotics. So, how will these models exactly look like? If we did not have LLMs, we could not have these foundational models. So, foundational robotics models have a structure which is very similar to large language models. In large language models, what happens is that if you type a question, the model gives you an answer in an auto-regressive manner. It generates one single token at a time. Here, you don't need to generate tokens, but you need to predict an action. For example, if I ask my robot to fold clothes, I don't need the robot to speak out to me that, okay, I understood, I need to fold clothes. I need the robot to actually go ahead and perform some actions. So, what people did was they took the existing LLM architecture and they added one layer on top of it called the action layer. And this vision language action models were born. What does a vision language action model mean? Well, let's rewind a bit and understand what are VLMs first. Vision language models are very similar to large language models, but they have a visual layer which understands images. And that is what makes VLMs very powerful, because now you no longer can not just can understand text, but you can understand these images also along with the text. So people use VLMs for a lot of applications. Now, VLAs are where we add one more layer to this, which is the action layer. So that's why these are called as vision language action models. So VLAs are being used to develop these foundational robotics models where the architecture is very similar to LLMs but with an added layer of action. Now, why this field is very interesting is earlier my thought process was that robotics is a field which is hardware driven. If you do not have access to hardware, it's going to be incredibly difficult for you to even simulate any papers to understand what people are doing. So, what I used to do was that I just used to watch news on the internet. What are labs doing? In no way I thought I could contribute. But now, where I'm seeing the field being headed, largely development of robotics foundational models is it has artificial intelligence at the core, which means that once you develop the software, 90 to 95% of the task is completed. In other words, software has again come at the heart of building or moving the frontier of robotics ahead, which is what makes me very excited because now I'm no longer hindered by the barrier of hardware because a lot of these models are built on top of LLMs. And we all know that we can now train and infer from LLMs and not just the foundational research AI labs like OpenAI, Anthropic, but all of us can contribute. Similarly, all of us can contribute on the software side. And today I have this hardware also with me, which is the SO101 robot. It's a cheap hardware developed by Hugging Face, and it allows you to perform a lot of different experimentations, try different AI models, develop policies on your own, etc. So we are seeing a paradigm shift in the field of robotics because of the development of these foundational robotics models which are built on top of the VLA architecture, and software has a huge role to play in this advancement. So the entire field is developing rapidly. There are models like Pi0, which was released, and it's a foundational robotics models which can do huge number of tasks. And when I started reading about all of this, I saw that Hugging Face has also made a huge contribution on the software side. They have a software GitHub repo called LoRobo. The LoRobo software developed by Hugging Face is incredible. It allows beginners to enter into the field of robotics and start developing their own policies and implement it on hardware like the SO101. To help you understand why I think the bridge between hardware and software has been diminished in the field of robotics, I want to give you an example where I demonstrate the principle of teleoperation to you. Teleoperation means that we control one robot by moving another robot. The same principle was used by the Neo robot as well, where the robot which you saw in the demo was actually controlled by someone in their company. So in teleoperation, we have a leader robot and a follower robot. I am going to move the leader robot and I want the follower robot to exactly mimic my leader robot. Why is this done? This is very useful to teach our follower robot about trajectories which it can mimic. And that's why this principle is very effective. The first time I did it, I was amazed as to how simple it was to use the LeRobo software and do this teleoperation. So I'm going to do this small quick demo in front of all of you, and I hope it works. Let's see. I'm running a small piece of script right now, and I hope it works. Let's see. Okay, so let's see. First, I'll just move this arm up. You can see the follower arm exactly mimics my leader arm. I'll now move the wrist. I'll rotate the wrist. Let me just open the jaw as well. This flexibility allows us to control the follower arm easily and help us to teach the follower arm to understand trajectories that we want it to follow. You can also lift it, lift down, rotate. So the entire follower arm I can control now with the help of the leader arm. It's amazing to see. Now, this is what I wanted to demonstrate to all of you to help you understand how easy teleoperation is. And it's also straightforward to implement policies in LeRobo. My main intention of making this video was to inspire everyone to join in the field of robotics. There are two types of people out there. People who are good in AI, they understand AI, but they are afraid to get into robotics because they think it's hardware based. The second type of people are people who are good in hardware, but they don't know much about AI. I want both these people, both these types of people to come together and join this field of robotics, because actually the bridge between robotics and AI has now gone, has been reduced, and software and hardware are being merged as we speak. And in the next 5 years, from the development of robotics that I have seen, it's going to increase a lot, and we might see a paradigm shift, like we saw with the launch of ChatGPT 2 years back. We might see the development of robust robotic foundational models, and also more common, we'll see household robots doing household chores. So the community is evolving rapidly, and I want to help uh, spread this message to everyone so that they can also contribute. Now, finally, the main reason for recording this video is also to announce the launch of our new course from Vijwara called Modern Robot Learning from Scratch. We are going to explain all the fundamentals of robotics and help you understand how to impart AI policies in these hardwares. The crux of this is going to be artificial intelligence, but it's going to be oriented towards robotics. And we'll have a lot of practical applications on these SO101 arms as well. Uh, Okay, so as a part of this course, we are going to cover different lectures, and every lecture will have orientation towards different policies, different concepts of AI ML. And we are going to see how diffusion plays a big role, how variational autoencoders, vision language models, all of these fields come together very beautifully in this field of robotics. And I want to transfer uh, this beauty to all of you as a part of this course. This is the first time Vijwara is launching a course related to hardware, because we are placing our bets on it. We really think that software and hardware are going to work together in the future. And we want this course to be the foundational course which helps all of you understand how AI can be integrated into robotics. Thank you, everyone. And now let's understand the course structure and curriculum briefly. What led me to develop this curriculum was a simple question. All of us have seen videos of highly complex and humanoid looking robots like Boston Dynamics, where we have seen these robots can do crazy stunts. And this might give us an impression that the field of robotics is doing very well. But the question which started bothering me was, if robotics is doing very well as a field, then why haven't we seen robots in our locality which can do simple tasks like folding clothes? And why hasn't the field of robotics become more commercial and easy to use? So I asked this question, and this led me to a quest. And through that quest, this curriculum has been developed. So let us rewind 50 years back when people first started understanding the problem of robotics. The first thing which came to everyone's mind was, let's take an example of a robotic arm. So the arm has many degrees of freedom. It can move up and down, it can twist, it can turn, etc. And for the longest time, robotics was a field which was all about understanding the mechanics of the robot assembly. The question that we asked was, if there is a specific path which I want my gripper, which is the end point, to move, how should the joints vary? To answer that question, you needed equations of motion for every single joint, and it led to a very complex system. The system was complex, but it was incredibly effective. We have sent people to Moon and Mars with these system of equations which people can solve. In fact, we had a course in our college called Kinematics and Dynamics of Machines, where we were taught to do all these things. But I quickly realized that this is not very practical. In many real life scenarios, you don't find environments which are predefined. Things can change very randomly. Also, for a beginner, it's very hard to understand these complex equations of motion apart from their limitations. So, next came reinforcement learning, where we learned from rewards. This is very similar to how humans learn about any new skill. Our parents don't just tell us this is how you ride a bicycle. Initially, we start riding the bicycle and we make a lot of mistakes. Then we learn from those mistakes, correct ourselves, and do better. And slowly and steadily, we learn the art of riding a bicycle. The same concept was applied to robots, and this was also very effective. People learn to do a lot of cool things using reinforcement learning because it was a system where you could solve that system without knowing the equations of motion. You just needed to know your states, actions, and rewards. But still, this field was very highly theoretical, and only people who were specialists in RL would work in this domain. You didn't see people posting on Twitter or LinkedIn that this is the robot I built using RL, like you do nowadays with LLMs and AI. So, why was that gap between experts and beginners? Later, another field came up which was called as behavior cloning. This is very similar to supervised learning, as I have said before in this lecture. So, here you are given an input output pairs and you learn to map the input to the output. And this technique started gaining traction around 2010. It is still a very popular technique, but again, you have some drawbacks with behavior cloning. The robot learns to imitate what it has been taught in the training. But what if in the testing it encounters suddenly something different, where it has no information about that in the training data? So again, you run into a problem. So, why this course now? One of the main reasons why I thought of starting this course is that I could see multiple trajectories converging in the future. The first is the development of LLMs. All of us are seeing the applications of that. It has been brought down to a level where anyone sitting in a lab can tweak an LLM, fine tune an LLM, do a lot of stuff with it. The second was the development of vision language models or VLMs. Very similar to LLMs, but now apart from understanding textual queries, you can now understand images as well. Third is the field of RL, which we have spoken before. And fourth is a very interesting field of diffusion models. Diffusion in a standard physical sense is where, let's say, I spray perfume in one corner of the room. I get the smell in the other corner of the room after some time. So the smell slowly percolates in the room. People have used diffusion techniques to generate images, videos. Now there are many diffusion language models also, which don't rely on predicting one token at a time but instead generate the entire sequence. Now, this course has all of these trajectories combined. All these trajectories have merged very nicely in the field of robotics. And we have come to a place where we can use LLMs, VLMs, RL, and diffusion models to build the software for our robots. And that is what attracted me to this field. And I really think that this is a starting point of making robotics accessible for all. What have LLMs done is that anyone sitting in any part of the world, if they want a machine to understand any language, they don't need to train the entire machine on their own. Someone else has already done the job, they just need to deploy it. The question is that can we build such foundational models, which we have done for language? Can we do the same for robotics? And just like we did with artificial intelligence, the first step is to collect a lot of data. Remember how the field of computer vision progressed? People first collected a huge set of data. They had no idea what to do with it. Take an example of the ImageNet data set, which has a collection of a lot of images. But later it was incredibly useful in developing the first deep neural network which could predict images very accurately. So, developing a data set is at the heart of democratizing model training. The same thing has happened in the field of robotics also. Similar to ImageNet, we have a data set which is called as OpenX. It is assembled from 22 different robots collected through a collaboration between 21 institutions demonstrating 527 skills. These institutions are Google, CMU, Stanford, Berkeley. So many institutes have participated and this data is collected. Very few people are aware about this. Now, this data can be used to train a foundational model from scratch. The question is that why aren't there any models developed yet? Let's have a look at it. These models which are developed are called as Vision Language Action Models or VLA models. These are the models which are very similar to VLMs, but we add one action layer on top of VLMs. So the trajectory which robotics is taking is very similar to the trajectory which AI started to take 10 to 15 years back. So now we are at the same stage where we were with computer vision 12 years back. And this is the starting point where these models will start to get better and better. Another model is the Pi Zero model developed by Physical Intelligence. This is also pioneered by scientists who worked in Google before. And you can see that this robot actually learns. So it's very so VLAs are the future of robotics, and we are going to understand how they work as a part of this course. Now let's come to the course curriculum. But before that, let's talk about the instructor. I will be the instructor for this course. Previously, I have taught the courses of reasoning LLMs from scratch and reinforcement learning. All of these courses are available on YouTube. And my teaching style is that I don't assume any prior knowledge. I tend to focus on the fundamentals. So I'll be explaining everything from scratch, and we will mix theory with practical in this course. So as I said before, this is the first course offered by Vijwara, which has hardware component inside it. Let's take a look at the curriculum now. We'll start with classical robotics. This will cover in one or two lectures. We will understand the drawbacks of classical robotics. Then we will move on to reinforcement learning. We will look at practical examples of implementing RL. We will look at algorithms like soft actor critic, Doraemon, HIL, SERL, and we will implement RL policies in a physical robot and see how they work. So this also I'll be taking from scratch. Then we will understand behavioral cloning, which is also called as imitation learning. We'll go very deep into diffusion models, variational autoencoders, flow matching, action checking with transformers, and all of this will have a practical component to it. That's why I have this SO101 robot with me, so I can implement it and I can see how the hardware works once this software is added. And then I'll focus on generalist robot policies. This is a very important part of the course. We'll understand about foundational models, RT1, RT2, OpenX, Droid, OpenVLA. We will understand the VLA architecture from scratch. We'll understand the Pi Zero model, small VLA, etc. This content is inspired from uh, the Low Robo Hugging Face tutorial, which is a 70 to 80 pages book which they have released. It includes curriculum at a broad level. but we'll be going into detail in all of the concepts which are mentioned in that book. Thank you very much, everyone. And I hope through this video I have conveyed the importance of robotics as a field, and why it is very important for people to understand that the gap between AI and robotics is now reducing, and both the fields are merging together very nicely. So, we'll be starting this course now. I'll be uploading lectures at a regular pace, and we'll be learning all of these concepts together. Thank you, everyone. Bye.